So good afternoon. I'd like to introduce today's speaker. Antonio Pedivellano has been a student in my group. It is a pleasure for me to say a few words before he starts his defense. Antonio has worked on some of the most challenging problems that we have encountered in the context of our research on structures for the Space Solar Power Project. And one of these challenges that you will hear about is the coiling mechanism, which had previously defeated several efforts by others. And this new coiling mechanism that you will hear about is only one among many of Antonio's accomplishments. In fact, what you will hear today, and those of you that look at his thesis will also see, is that Antonio has demonstrated many times that he is fearless and unstoppable. And these are characteristics that are found in many GALSIT PhD students. These are characteristics that we as faculty at GALSIT are proud of to see in our students. Now, I also have to warn you that Antonio also has another characteristic, and that is that I have yet to find a problem that Antonio will find to be difficult. So everything in his presentation will appear to be relatively straightforward, and that is just a common characteristic to all of the problems he works on. On the whole, they are not really difficult. It's just that it is clear to those that appreciate these matters and look at the details of how much work it takes to make things work in certain particular ways, that yes, actually, it does take a lot of effort, and sometimes some of these problems are very nearly impossible to solve. So you will see examples of that in today's presentation. And with that, I would like to hand it over to Antonio to start his presentation. I would also like to welcome, I heard that his brother is listening from Italy. We appreciate the fact that you are joining us at clearly a very inconvenient time for you. And I am sure that you will enjoy the experience of listening to this presentation, you like everybody else. So with that, over to Antonio. Antonio, please go ahead.
Thank you, Professor, for this introduction, and good afternoon, everyone. Good night to the people in Italy who are listening as well, and welcome to my PhD defense. Today, I will talk about my research, which is about the deployment dynamics of thin shell space structures. Well, my advisor is clearly Professor Pellegrino, and my thesis committee is composed by Professor Ravichandran, Professor Darayo, and Professor Lapusta. And before starting, I'd like to tell you about the main theme of this thesis, which is the idea of developing structures that are larger and lighter for space applications. And in particular, the type of structures that we're dealing with today is thin shells. Where you will hear more about it in a bit. One of their characteristics is that these structures can be elastically packaged into a small volume, and once in space, they can self-deploy. And one of the main challenges that we are trying to address today is to predict and understand the dynamics of this deployment process. So let's just start by understanding a bit what these shell structures are. And I'd like to start with a problem that I'm sure most of you have found at some point. How to hold a slice of pizza without dropping its toppings. Now, most of you have realized at some point that if you hold the pizza this way, by just bending the crust, your pizza slice becomes much stiffer and it remains straight. And this is really the key idea behind the shell structures. We're talking about structures that achieve very good mechanical performances thanks to their smart geometry. And by smart geometry, I mean that they really use curvature. Here I'm showing several examples of such structures in engineering. On the left, there are spherical pressure tanks. There are also applications in aerospace for airplane fuselages and examples in architecture. So what's common to all of them is that they're using a curved geometry. And because of this, they can be very thin-walled, which makes for lightweight structures. And as you can expect, lightweight structures are essential in space. And in particular, thin shells are used as deployable booms up there. These booms are essentially like beams, so they are extended in one direction. They have a curved cross-section, and they're very thin. Here we're talking about a few tens of microns. And because they are so thin, the cross-section can be flattened elastically so that you can fold them or you can roll them. And this allows them to be packaged in very small volumes to fit into a rocket and then deployed in space. And once they're deployed, they recover their original cross-sectional geometry, and therefore they're capable of bearing excellent loads. Because of these characteristics, they're used often to deploy thin membranes. And here on the right, you can see an example of the rollout solar array, where you have this flexible blanket with photovoltaics on it, which is supported by two deployable booms along the edges. And another example for square architectures is a solar sail that you see here at the top right, where you have a very thin membrane that is supported by 4 diagonal booms. Now, what's common to these two architectures is that in both cases, the membrane has no bending stiffness. And so in order to remain planar, you actually need to apply some tension to it. And this tension is applied by the deployable booms, which are therefore loaded in compression. Here at Caltech, we've been working on a different architecture, where you are using these thin shell components as bending stiff elements rather than compression elements. But let me just give you some more context about it. This is also part of the Space Solar Power project here at Caltech. The idea is fairly simple. We want to collect solar power in space, and we want to send it to Earth. Now, this idea has been around for like 50 years, and yet today there is no system like this. The main reason is that the other concepts that have been proposed so far were just too heavy, too complex, and too expensive. And so the way we're approaching this problem here at Caltech is through modularity and lightweight structures. As you can see in this concept here, we envision a system of 3 kilometers by 3 kilometers in space. That's huge. And it's made of a constellation of 60 meter by 60 meter spacecraft like this one. The basic structural unit of this spacecraft is the strip, on which we have many tiles, which are our functional elements. And these tiles, which are flexible, combine both solar cells to collect solar power and antennas to radiate this power to Earth. Now, today, I'd like to focus on the architecture, on the structural aspects of this architecture. So let's take a closer look at this spacecraft. As you can see, it's square in geometry. It's made for triangular quadrants. And what's unique about this structure is that instead of having 4 diagonal booms running along the diagonals, we have distributed many thin shell components over the entire surface of the structure, and we have connected them in a space frame. And you can think of the space frame as a skeleton, a bending stiff skeleton that supports our flexible membranes. And as you can see here at the bottom, the basic structural unit that I mentioned before is the strip, which is composed of 2 longerons connected by several buttons and with this membrane on top. Now, of course, you cannot fit a 60-meter spacecraft in a rocket, and so you need to package it. And the packaging scheme was proposed a couple of years ago, and it's inspired by Kirigami. It consists of a 2-step approach. You start from your deployed configuration in here. You first Z-fold each of the 4 quadrants to get into what we call a star shape, and then you wrap each of the 4 arms of the star shape to get into this cylindrical configuration. And to deploy the structure, you follow the same path, but in reverse order. Now, what's interesting here is that when we are in the star shape and we want to reach the deployed configuration, we can do a strain energy deployment, which means if we just let the structure go, the structure is capable of reaching this configuration by releasing the strain energy. However, this process needs to be understood. And as you can see here, well, this concept was formalized in 2016, but the research on this problem started earlier than that. And ever since, we started a lot of research trying to make this concept real. So really behind what I'm going to show you today, there is the work of many people over many years. And it all started with the packaging concept that you can see here, and it was demonstrated just on membranes. Then we started studying individual components of our system, the longerons first, then the strips, and there were concepts of deployment mechanism to control this packaging process. And it was only in 2019 that we actually built our first 2-meter scale prototype. And that was about the time when I joined this lab and I started working on this type of problems. And if you fast forward to today, here we are. We are developing our flight demonstration of this deployable structure and its deployment mechanism. And really my research bridges this initial structure that we built and we had no idea of how to package. And there's actually a flight demonstration that we call DOLCE, which stands for Deployment on Orbit of Ultralight Composite Experiment. And we have been working on this for a couple of years, and it's set to launch next year. So that's pretty exciting. So today you will hear the steps that have taken this structure from here to that. And the way we are doing that is through a combination of experiments and simulations. From an experimental standpoint, well, ground testing is what is done for most space systems. However, when you have this very large area structures, you are running a lot of trouble. One of the main reasons is that these structures are extremely lightweight and they're designed for space. So they're not designed for being operated in terrestrial application under gravity. And therefore, many of them cannot even withstand their own weight. And so you need some sort of gravity compensation in order to support your structure during deployment. And here I'm showing just a few examples where people, for example, use cords with counterweights, they use balloons, or they do deployment in microgravity during parabolic flights. On the other hand, you also have effects of air during ground testing. And what many people do is to deploy their structures in vacuum. But as you can expect, doing experiments in vacuum chambers is complicated, it's expensive, it takes time. And so many people actually do that in air. And so the bottom line here is that during ground testing, you will never capture the actual behavior that you're going to see in space. And the only way to do that is through numerical simulations. And in the past, people have done simulations of large structures, especially in the context of solar sails. Here, for example, you see a simulation done for the Icarus solar sail. And those models were simplified. So initially, they were using the particle method. Then they developed their own finite element code. And these models were very good at capturing the global behavior of the structure, but they were still missing the local effects. For example, the contacts between membranes. And really, in our case, we are dealing with shell structures. And the behavior of shells is all about local effects. For example, contacts are very important. And when you fold one shell, you start having localized deformations. So if we really want to predict the behavior of our structure in space, we will need high fidelity models of the entire structure, which is something that no one has done before. And this really brings me to the objective of my research, which is to enable thin shell architectures for large area deployable structures. And just to be more specific, we want to do this in 3 steps. First, we want to observe this behavior experimentally. And in particular, we are asking what happens when you have multiple of these thin shell components folded together and you deploy them simultaneously by releasing their strain energy. But in order to do these experiments, you need actually to package your structure first. And so we need to design solutions to implement the packaging scheme on these structures. And finally, we want to develop numerical models that are capable of capturing the complex behavior of the structure even during ground testing. And these models can then be used to support the design of new structures, as well as to verify their performance in space before launch. The way we are approaching this problem is in 3 steps. First, we're going to look into a thin shell strip, like the one that you see here. So this strip is initially folded, and then we deploy it under strain energy. Then we will move into the space solar power spacecraft, and we will talk about the implementation of the packaging scheme on the spacecraft. And finally, we're going to look into the deployment dynamics of the spacecraft. But starting from the first topic, here you can see on top right, one of our 1.7 meter scale prototypes that is folded in a star folded configuration. And when we started looking at this problem, we say, well, let's try to model this entire problem at once. Let's build our finite element model. And I started doing that around my candidacy. So it was a couple of years ago. I already had my first model. But then after a while, we realized that having a model is easy, but having the right model, that's very complicated. One of the problems was that we have many strips stacked together. There are many interfaces, there are many joints, there are many parameters in this problem, and it's very hard to isolate each one of them on this sort of structure. And that's why after a while of attempts and lots of efforts, we decided to take a step back and look at a simpler version of the structure. We wanted something that could capture most of the challenges without actually bringing all this complexity. And this is the strip. As we said, our structure is modular, it's made of several strips. And so we just took a single strip from our structure. We simplified the geometry. We made it rectangular rather than trapezoidal. And we placed 2 elastic folds on it to mimic what happens in the real structure. And on this strip, We built several versions of it, and we did a lot of experiments to validate all of its behavior, not only the intrinsic behavior of the strip, but also the effect of the membrane on it, the effect of air, and the effect of the suspension system. And we built our finite element model onto the strip. So let me just give you some more details about this deployment study. So here you can see at the top our strip. It's about 1 meter long, and it's made of two longerons that you see here. They have a track cross-section, which is made of two circular arc flanges connected on a flat web. The longerons are connected by several transverse buttons, and there is a membrane on top. So this is just a dummy membrane. It's just to take into account the effect of a real functional layer. But this membrane has no functionality yet. So we built two models of this strip, one with the membrane on top and the other one without, just to understand what the effect would have been. And we built a suspension system for this experiment, where we have cords running over pulleys and connected to counterweights. Now, in this case, we are deploying our structure against gravity. So this is not a gravity compensation system. Really, in this case, we are accepting the effect of gravity, and we built a suspension system that is easy to characterize in a very deterministic way. And the initial condition for this problem are set by two parameters, essentially. One is the distance between these two elastic folds, and the second one is the angle of the elastic folds. In particular, this angle is controlled by two other parameters, this initial height h0 and the mass of the counterweights m. So we started doing over 100 experiments, testing all different combinations of these three parameters to understand what their effect was on the deployment of the structure. And well, we found that in most cases, the behavior of the structure was consistent. So qualitatively it was the same. And so what we picked for the study was a set of parameters that is representative of a wide range of conditions. So we built our experiment, and you can see it in here. We have the structure with the membrane in here, inside an aluminum frame that contains it. And on the aluminum frame, we have pulleys, miniature pulleys to have very low friction and inertia. We have a release mechanism that is composed of two linear actuators. So this release mechanism essentially holds the structure in its folder configuration, and then we actuate it, and it releases the structure in a very synchronized way. And then we have a metrology system with two high-speed cameras that you see here. And with these cameras, we take 500 images per second, and we use them to actually get quantitative measurements out of these experiments. And as I mentioned before, we were interested in understanding what the effect of air was. And so we did our experiments in an altitude chamber, of which you can see the inside in this picture. And we operated this chamber at about 7% of atmospheric pressure. So this is not properly vacuum, of course, but for the purpose of our experiment, we found that at this pressure, the effect of air became negligible for our structure. So that's what I'm going to call vacuum from now on. And once we have the pictures from our experiment, what we do is we implemented an algorithm to reconstruct the shape of our structure from there. And the way the algorithm works is that we start from our images. And as you can see in here, there are many white dots on our longerons. That's a speckle pattern that we painted in it. And we use digital image correlation to convert the speckle pattern into point cloud. So we know the coordinates, the 3D coordinates of many points on the structure. And then we take each longeron, we project its point cloud on a plane. We find the midline for this point cloud. And we compute the local tangent to each one of the points, and then its orientation from the x-axis. So we get the plot that we have here. So now here it's interesting to notice that we have basically three areas of uniform orientation. So at the center, the strip remains horizontal. And then at the two ends, we have equal and opposite angles. And essentially, the strip behaves like three panels connected together by hinges that gradually open. Now, if you take the numerical derivative of this plot, you get the distribution of longitudinal curvature on the longeron. And again, here you can see that there are two peaks, very sharp. They correspond to the location of the elastic folds. And this suggests that for this problem, essentially the structure behaves as a collection of rigid parts connected by elastic hinges. And we're going to use this observation later in this talk. So these plots are for a single snapshot from our experiment. Now we can repeat it for the entire duration of the deployment. And what we can get, for example, is the angle of the elastic folds that you see in this plot here. So there are two lines corresponding to the two longerons. So let's just look at one of them. And what you can see there is that we are averaging the angle, the orientation of the two ends of the structure. And that's why you get two lines for each longeron. And you can see that it's pretty symmetric during the deployment. So this angle starts from about 45 degrees for this case, and it decreases to 0. And when all the four folds on the strip became 0 for the first time, we defined our time of deployment, which for this case is slightly more than 300 milliseconds. Also, after this point, you can see that the angle remains 0. So basically what happens is that the elastic folds latch, the longeron becomes straight, and it doesn't buckle again. Now, if you look at the elastic folds here at the bottom, and we track the location of these peaks over time, you see that the elastic folds remain stationary during this problem. And this is not an obvious result, because we know that there are many other problems in which instead you have significant propagation of the elastic folds. So it's interesting to see that in this case, this doesn't happen. And now that we have our algorithm in place, we can finally look at the experimental results. So first, I'm going to show you the results for the strip without membrane. And I'm plotting here the angle of the elastic folds. So here in blue, we have the deployment experiments in air, and in orange, we have the ones in vacuum. And you can see that in this case, there is basically no effect from air. The behavior is pretty much the same. However, if you look at the strip with membrane, now you have a significant difference. And in particular, the deployment in air takes about 70% longer than in vacuum. And this means that for that type of structures, you cannot neglect the effect of air. And another thing that I'd like to notice is that if you compare now the orange lines between the two plots, that's the behavior in vacuum, they're qualitatively the same. So this means that essentially the effect of the membrane is simply to add more inertia to the structure, but they don't contribute to changing the response of the strip. And this makes sense intuitively, because our strip is basically loaded in bending. And we know that membranes don't have any bending stiffness almost. They only react to in-plane shear. And therefore, for this specific case, they have no effect on the deployment. Well, now let's see if we can capture all of these effects in simulations. And this is the finite element model that we developed in Abacus. We are using an explicit dynamics solver. And since we saw from experiments that the behavior of the structure is mostly symmetric, we are only modeling alpha the strip. So here you can see the symmetry plane. A few words about this model. We are modeling the longerons as shell elements, the buttons as beam elements. We have 1D connector elements for the suspension system. And for the membrane, we're using membrane elements with a special material formulation that also accounts for wrinkling. And that's called the IMP model. It's been proposed many years ago, but we're using an implementation that was published by Deng and Pellegrino in a paper from 2012. And for this type of simulation, the computational time is in the order of a day for the structure without membrane, and about 3.5 days for the structure with membrane. So they're quite intensive. Another thing that I like to mention is the effect of air. As we said, air is important for these problems. And if you really want to resolve this interaction, you need coupled structural and CFD solvers. That's what some people do. However, those are very computationally expensive, and we really wanted some simple way of dealing with this problem. And so we are taking inspiration by some research that has been done on the vibration of membranes in air. Those studies identified two main contributions from this interaction. One is an increased inertia to the structure, because you can think that as you move your structure through a fluid, you are moving some masses of air with it. And so that results in added mass. And the second effect is air damping, because you are basically losing some energy in this interaction with the flow. So for the added air mass, we used a simplified method based on geometric considerations to define an air volume around the structure, and that's the half cylinder that you see here. We compute the mass of air within this volume, and we distribute it uniformly over our structure. Of course, this is a very approximate approach, but something like this has been previously done for membranes, and it worked fairly well. And here, the idea behind choosing this half cylindrical volume is that we expect the effects of air to be basically zero at the edges and to increase as you move away from the edges. And that's why we ended up with this cylinder. Regarding the air damping, if you look at our problem from an aerodynamic standpoint, it's very similar to the problem of a flat lamina with an incident flow perpendicular to the lamina. And in that case, where in aerodynamics, people use a drag formulation where the drag increases with the square of the relative velocity. And the proportionality factor is a drag coefficient, which there are many examples in literature for many different geometries. In our case, our strip is mostly planar. However, at the edges, we have these curved longerons, which make its behavior look more similar to that of the geometry that you see here, which is an half cylinder with the concave side facing the flow. And that's the geometry that we took as a reference for our drag coefficient. And now let me just spend a few words on the way we approach this problem. And this is a pretty general way of dealing with this type of deployment problems. You always start from your initial undeformed configuration. First, you fold your structure. And so in our case, we are creating elastic folds by pinching the longerons locally at the locations that we want. Then we use rigid cylinders to push our structure down, and we get into the folded configuration. And then we remove the cylinders, and we let our structure deploy under strain energy. And the main tool to observe what happens during this simulation is the energy balance that you see here in the plot on the right. In this case, there are a few indicators that I like to mention. The first one is the total energy that during the simulation remains 0. And that's a good sanity check. It means that we are not losing or gaining energy artificially. Then I'd like to highlight the strain energy, the line in bold. And here you can see that the main contribution to the strain energy really comes from just flattening the cross section in the very first step when we create the folds. Then we have an increase of the strain energy as we fold our structure because we are increasing the angle of the elastic folds. And after an equilibrium step in which we achieve equilibrium, we start deploying our structure. You see that the strain energy decreases as the structure becomes flatter and flatter. And at some point, there is a sharp decrease. And this is when we have snapping of the elastic folds. So here, basically, the elastic folds disappear, and the remaining strain energy is associated with the elastic vibrations of the structure. And we dissipate these vibrations in the final equilibrium step. One final remark is that if you look at the kinetic energy now, the red line in bold, you see that we are not doing a quasi-static folding process. And that's just because it will take too long. However, what's important is that at the end of the equilibrium step, you have no kinetic energy in your system, which means that you have actually achieved full equilibrium. And now let's look at the comparison with the experiments. Here we are showing different cases, so just don't focus on any one of them in particular. But what I like to show you is that we tried different combinations, the structure with and without membrane, in vacuum and in air. And we also tried different masses in the suspension system. And for all of those cases, we found an excellent agreement between the experiments in gray and the simulations in red. So that makes us confident that actually this model works and is predictive of the behavior of this type of structures. Well, now that we have this, we can try to move towards our solar power spacecraft. But if you want to do experiments on this, you first need to package it. So that's the problem that we're going to discuss now. And here we have the first fundamental question to ask. Well, how can we store our structure in a robust and repeatable way without breaking anything? And this is not a trivial question, because the first time that we built one of our deployable structures at the 2-meter scale, and we tried to actually fold it to do this process, starting from the deployed configuration into the star shape, well, we found this process incredibly hard. As we were trying to fold our longerons, there were buckles appearing at random locations. So it was a pretty messy process, and we ended up actually breaking some of the components on it. So that told us that actually we needed a systematic way of folding our structure, and that's one of the things that I'm going to discuss today. The second thing is that, well, now that we have this star shape, how do you actually get into the rolled configuration? And for this, we will need the deployment mechanism, and we're going to discuss that as well. So let's just start with the first step of this packaging process. So we have our deployed structure, and we want to get into the star shape. The approach that we use in this case is to look at the kinematics of this problem. So here on the left, you can see the model of our deployable structure. We have 12 strips in total, and they are arranged in 3 concentric squares. Now, if you just isolate one of these squares, we get something like this. So now we have 4 strips interconnected together, and we're assuming that they are hinged to each other. Now, the key idea here is the following. We know that as we fold the shell structure, you're going to have elastic folds. So let's just put them at places that we want. And that's what we did. We placed 2 elastic folds on each one of the strips. We made them symmetric just to reduce the number of variables in our problem. And now, as you try to fold our structure, if you remember now from the strip problem, you saw that essentially all the deformation was taken by these elastic folds, and everything else was mostly planar. It had almost 0 curvature. And so as a first order approximation, you can take this structure and convert it into an equivalent mechanism, where you basically replace each of the elastic folds and each of the hinges with a joint, and everything else in between is made of rigid links. Now, if you look just at one of these joints, we have 2 degrees of freedom there. One is the angle, the rotation about the fold axis, which is this angle beta. And the second one is a torsional angle, psi, which takes into account that we have actually a flexible structure and torsion is possible. And so for this system, we end up with 24 degrees of freedom. Now, the way we are going to solve this is an approach that is very well known in the robotics community. And essentially, whenever you have this sort of closed chain, you have to impose some loop closure equation to make sure that your chain remains connected as it deforms. And the formulation that we are using here is shown in this green box. And essentially, what you have here is this transformation matrices T, which combine both rotations and translations. And what this equation tells you is that if you start combining coordinate transformation between following links until you get back to the original point, you should retrieve your identity matrix because you're back at the starting point. Now, this is a matrix equation, so we have 16 scalar equations. However, only 6 of them are linearly independent. And that's because you can always express a coordinate transformation as 3 rotation components and 3 translations. So that's why we only have 6 equations. This is a highly nonlinear equation. And so to solve it, we used an incremental solution approach that was developed by Gann and Pellegrino. And now let's just go to the results. And let's look at the results for our single square loop. Another thing that I'd like to do here is to simplify a bit the problem. So we started with 24 degrees of freedom, as you remember. And if we impose 4-fold symmetry, now we are left with only 3 degrees of freedom, which are the fold angle that you see here, the hinge angle here in green, and the torsion of the strip, the twisting, which is not shown in this diagram. And the solution that we get is shown in this plot. And it's fairly simple. So as you increase the hinge angle here, you are decreasing the fold angle from 0 to minus 45 degrees. Now, there are a few interesting things about this solution. The first of them is that there is no twisting. This red line is 0. And that's not by construction. It was actually free to twist. That's just a solution that we found. And that's nice because it means that we don't need to apply any torsion to our strips. Our functional elements don't like it. The second thing is that our solution here, so this relation between the internal variables of this chain is independent of where we place our elastic folds. So in this case, we place them here at the ends, but we could place them anywhere else and it would be the same solution. And the third aspect is that this solution is actually unique, which means that if you try to fold your structure in a 4-fold symmetric way, there is only a way to fold it. And this is important because it allows to have a very deterministic folding process. And just to show you an animation of what this process looks like, it's essentially a combination of folding of the strips and a rotation out of plane. So this is the type of motion that we have for this type of structures. But now that we have the solution for the full square, for the single square, let's go back to the original problem that was how to fold the full structure. Well, in this case, just to give you some intuition about this problem, so for each one of the squares, the solution is still the same as I just showed you. However, now we have additional constraints because now the strips are connected to each other by cords running along the diagonals. And also we have more degrees of freedom because now we can also control the rigid body motion of between squares, as well as we can decide the sequence by which we want to fold our squares. So let me just show you the result that we came up with. And so this is a 2-fold step process. First, we fold the outermost strip and the middle one, and then the inner one as you see here. And now we have our design. So how do we implement this design on the real prototype? So there are 2 things that we took from this design. First of all, the location of the elastic folds, which are the solid lines that you see here. And the second thing is the sequence, the 2-step approach that you just saw. And now I'm going to show you a time lapse of us folding the structure. So the way we impose elastic folds here is by putting hairpins on our longerons. So here you're going to see the first step of the folding process in which we fold the outermost and the middle squares. And this is it. And again, we add more hairpins to constrain the structure and to stay into this configuration. And now in the second step, what you're going to see is that we're going to fold the square, and one of the strips will disconnect a bit from the others. Now, this is just to remind that the actual structure has a bit more degrees of freedom than what we had in our design. In particular, the strips are not really hinged together. They're hinged to a cord. And now you can slide actually this cord between strips, and so you can disconnect the strips without breaking them. So this means that actually there are some aspects that the kinematic model doesn't capture. However, by using the right handling of the structure, you can actually match that design fairly well. Now that we have the star shape, we want to do the final part of the packaging process, the coiling. And in this case, well, the main challenge is that thin shells don't like to be coiled. And when you try to coil them, they actually undergo lots of instabilities. And I'm showing you some of them here. The reason is that essentially, as you coil them, they store strain energy because they're bending stiff. And so they try to find a minimum energy configuration that, believe me, it's never the one that you want. And so you start having buckles, which is shown here, where you form this pattern, periodic pattern of high curvature regions with other connected by portions of zero curvature. And that's bad because your nominal radius of curvature should be the radius of the hub, 2 inches in that case. And actually you have higher curvature, which means that if you have some brittle components in your structure, you may actually damage them. And the second type of instability is blossoming, when you have your thin shell coiled around the cylindrical hub. So you try to deploy this shell by rotating the hub, but actually the shell doesn't deploy, it just expands inside the deployer. And this is particularly true when you have some compression force applied at the tip of the shell, which is, for example, what happens if you are trying to deploy a membrane. And in this case, the risk is that you jump the mechanism first, and then you can have a very high curvature at the root. And so again, you break your structure. And so people have come up with different solutions for deployable booms. And here I'm showing different kinds of stabilization that have been used in the past. One of them is the radial force stabilization, in which you basically apply radial forces at discrete locations around your structure to push it against the hub. And this is by far the most common approach because it's the simplest to implement. You can, for example, use some spring-loaded rollers. However, here you start having a lot of non-uniform forces, which is not good for brittle components, and you don't really suppress buckling. The second approach is the tension stabilization that you see here. And in this case, you are pulling on one end of your shell, and you apply a counter torque on the hub. Now, this in principle is very nice. You get a uniform state of tension in your structure. However, the implementation of this concept is pretty challenging. And other people have tried it, we tried it, and it didn't work very well. And so the concept that I'll be focusing on today is the pressure stabilization that you see here. And in this case, you have your structure in black, and that's co-coiled with a secondary membrane or thin strip of metal that is shown here in red. And this thin membrane is connected at one end to the central hub, and at the other end to a secondary cylinder that you see up here. And so by applying some torque to this cylinder, you're going to have some tension in the membrane, and therefore you are basically compressing the structure to conform to the hub. And so this is the concept that we used. And here you can see our idea of this deployment mechanism for our structure. The way it works is that we have 4 inner cylinders that you see in here. They rotate together. By rotating, they control the coiling and uncoiling process. Then you have the coilable structure here in light gray. You have the membrane in dark gray. And we have 4 rollers that are stationary and they're placed outside of the mechanism. And so these rollers have some torque applied to it. It can be either passive using some springs, or it can be active using motors. And the way this stabilization works, again, if you look at this diagram on the left, you have some tension in the membrane because of these motors, or these rollers. And if you look at the free body diagram for this system, this tension in the membrane is balanced by a pressure distribution which is applied by the membrane, by the structure, sorry. And so the structure in turn is pushed against the inner cylinder, and that gives us the right stabilization that we want. And another feature of this mechanism is that we are using force control, which means that we are independently applying the same torque to all of the 4 rollers. And this is extremely important because now we don't have 4 independent pieces of the structure. They're all connected together. So if the structure is not perfectly symmetric, or one of the membranes is longer than the others, and you use displacement control, you end up with some of the membranes getting slack. In our case, instead, using force control, we make sure that our mechanism is robust against any type of misalignment. And so the membranes never get slack, and this is much more reliable than other concepts. And this is the implementation. So this was the first prototype that we built. It's a proof of concept, and it has the deployable structure inside. So you can think of this 1.7 meter structure that gets coiled in a diameter of about 20 centimeters. So that's pretty nice. And just to mention a few features of this mechanism, we have a motor at the center that rotates the inner cylinders. We have active rollers in this case. So each one of the rollers has a motor inside. And we have a release mechanism at the top, which has a single actuator that you see here. So the release mechanism has 4 latches here in orange. And what happens is that when you actuate it, these latches open and the roller assemblies rotate about an inch that is at the bottom. And so this basically opens the mechanism. And this is essential to actually move to the next step of deployment. So after you uncoil your structure, you need to unfold it for it to be planar. And so you need to open the mechanism. And so this is the way we do that. So let me show you a video of this coiling process. Here we have the structure initially in the star shape, and we gradually coil it. And this deployment was done at the end of 2019. So we spent approximately a year trying to make it work. And well, it worked. And after that, we've been doing experiments, this type of experiments on many structures and with a different version of the mechanism as well. And it worked in a very reliable way. I think we have some internet problem. Hello?
We're hearing you fine, Antonio.
Oh, okay. No,
it's just that your image is frozen on the screen. Just try the next slide and see what happens.
Okay, sure. Sorry.
We may be okay, or maybe it may not be. So let's just see what happens.
Okay, for now it's fine. Okay, well, now we have our structure coil. We can take care both of the coiling and uncoiling process. And so we can get into the star shape. And now at this point, we want to study the deployment of the structure from this configuration.
Try turning off your video.
I did. It says that Zoom is not responding. Okay.
Okay, try the next slide.
Fine.
We're seeing slide 34 right now.
Me too. Yeah.
Okay.
Okay. So let me show you a bit this problem of deploying the structure. So we have the structure in the star shape you see here. We have the deployment mechanism in a very idealized form. And we have 4 core tensioning systems along the 4 diagonals of the structure. So these are responsible for actually supporting the structure at deployment during ground testing. Now, if you look at this problem from a kinematic standpoint, we can use the same model that we showed before. And we get something like this. Of course, the kinematic model doesn't know anything about energy. So now there are many questions that remain open. For example, how long does the deployment take? Does the structure actually have enough energy to fully deploy? Does it get tangled? How does it interfere? Does it interfere with the mechanism? And so to answer all of these questions, we approach this problem both through experiments and simulations in finite elements. So let's start from the experiments. Now, we did our experiments in the cast arena. What's nice about it is that they have an amazing motion capture system distributed over the perimeter of this test area. And these cameras can track the locations of retrofractive markers distributed on the structure, and they return in real time their 3D coordinates. So this is very nice because it basically allows you to track a large number of points in your structure with very little post-processing. And because of this, we distributed over almost 280 markers on the structure, and we captured the images at 180 frames per second. Now, if you look at the test article, this is what it looks like. We have our deployable structure in the star shape. You can see that this structure is different from the one that we use for the folding part. So this is a new version of the structure and doesn't have membranes on top. So this makes the deployment a bit simpler to predict and also a bit more deterministic. And also the deployment mechanism looks different. So this is the next version of the mechanism based on the same approach, so on the same concept, but this is actually the one that is designed to survive the launch environment. So this is the one that is undergoing the qualification test to be ready for the flight demo. And of course, as you can expect, all of this work couldn't be done without lots of support. So actually, the Dolce team developed the structure and the mechanism. So behind this experiment, there are many months of work by many people. It was a team effort. Well, one of the main differences between this mechanism and the previous one is that we have individual release mechanisms on each one of the 4 rollers. And here you can see one of these actuators. So I guess let me just show you a video of what this deployment looks like. Here we have our structure initially rolled inside the mechanism, and we are gradually expanding it. And I think in this 40 seconds of video, you're going to see my entire research coming in a single place. Because to get the structure folded and packaged, you actually need to use what I showed you before. And to deploy it, now you're going to see all the work that has been done. So now we have uncoiled the structure and we are in a star shape. What you're going to see next is the rollers releasing and the structure expanding out. So this is pretty fast. It's less than a second, so be ready for it. And this is the unfolding process. And now let me show you a slow motion video of the same experiment. So you see the mechanism opening and the structure gradually expanding out. And you can also see that there is really a lot going on in this experiment. And so one of the first questions was, well, how do you describe this process? What are the right metrics to describe it? And we came up with several metrics that we thought made sense. One of them, for example, is the distance of the corners of the structure from the center. And you can see this distance here. It basically gives us an idea of the deployed sides of the structure over time. And you can see that this size increases gradually over time until it reaches a maximum value after about 700 milliseconds. And then that's our deployment time, basically. And you can also see here the mean value in black. And this overall process is very symmetric and pretty repeatable. The second metric that we chose is the angle of the elastic folds on these outermost strips. And those are the 2 angles, θ1 and θ2, that you see here. And we chose this because it's what is the way generally folded shells are described. And what you can see is that this angle decreases from about 90 degrees at the beginning to 0, and then it remains 0. Again, this means that we are latching our structure. And then another thing to notice is that the 2 angles on the longerons of the same strip are approximately the same, which means that there is very little torsion in our structure. And finally, we looked at the envelope of the center strip heights. So this is basically the locus of the highest and lowest points of the structure as a function of the distance from their center. And this has significance for 2 reasons. From a theoretical standpoint, it tells us that this deployment really doesn't happen in a plane. It's a highly 3-dimensional motion, which spans an area of about an height of about 550 millimeters. From a practical standpoint, this also tells us what's the keep out region for our deployment mechanism, and not in order to deploy the structure without interfering with anything else. So in a real system, if you place some other component into this area, you're going probably to interfere and prevent the deployment of the structure. So this is very important from a practical standpoint. And now that we have our experiment in place, let's look at the simulation. So what we try to do here is to bring as much as possible from the strip deployment study. And so many of the parts of the structure were modeled in the same way. However, of course, there are many new challenges to solve. So let me just give you some details about it. So first of all, we assumed 4-fold symmetry on the structure. So we are only modeling 1 quadrant as representative of the entire thing. We are not adding any air effects because as we found in the first part of this talk, we don't have membranes, and in that case, the effect of air is negligible. And for this type of simulations, the computational time is in the order of 4 days. So it takes a while. And the most challenging part of this simulation is folding, because once you get your structure folded in the right configuration, then it becomes easy to let it deploy. And for the folding part, one of the challenges was that we cannot simply use the same process that I showed you for packaging the real structure, because it's a 2-step approach and it will take too long. So we had to find a more efficient way to fold the structure. And the way we are doing so is by Z-folding all of the strips at the same time and having a fold at the center. So this process is controlled by controlling the difference in height between the control points that are placed on the mountain and valley folds of the structure. And so, of course, this folding process now is not compatible anymore with the chords running between strips. And so we deactivate them for this part of the simulation. So once we get our strips rotated into this configuration, we simply push the structure towards the center of the mechanism, and we close the mechanism around it. And we get into this configuration, and we finally apply all the loads that we need. In particular, we apply gravity. We activate the chords between strips, and we apply tension to the chord retractor system. And with this, we have the structure ready for deployment. So let me just show you a comparison between the experiments on the right and the simulation on the left. And this is what happens. So the rollers gradually open, and you see that the squares are deployed out of the structure almost one at a time. Now, of course, it's difficult to compare them, I know. But one of the differences that I'd like to highlight here is that, let me show this video again. Sorry, yeah. Is that in the experiment, the rollers don't really release at the same time. There is a little bit of delay between them. Whereas in our case, we are using a fully symmetric model, and therefore they ideally release at the same time. And this is an important difference that affects a bit the results that you're going to see next. So let's compare the simulations with the experiments, and we will use the same metrics as before, just to be consistent. So here on the left, you see the evolution of the height of the distance of the corners of the structure from the center, as before, this distance r, where in solid lines we have the experiment, and in dashed lines you have the simulation. And you see that there is globally pretty good agreement between the two of them. We capture the right deployment time. There is a little bit of difference at the beginning, because as I said before, at the beginning, the simulation deploys faster because the mechanism opens in a synchronized way. Now, if we look at the angle of the elastifolds, the second plot here, you can see that there is very good agreement between the two of them. And this tells us that essentially we are capturing very well the elastic response of the strips. And so really the only difference between experiments and simulation is in the rigid body motion of the structure. And you can see this, for example, in the envelope of the center strip side. So again, here we are tracking in red the highest points of the structure at the center and the lowest in blue. And you can see that simulations overpredict this deployment envelope in both directions, just by virtue of this a faster release of the rollers. So there is some extra work to be done there for sure. And with this, I'd like to wrap it up. Let me just summarize what we discussed. So we started from the study of a single strip. We saw how we can fold and deploy that. And we observed several effects of interest, like the effects of the membrane, the effect of the hair, and the suspension system. And we captured all of them very well in simulations. Then we moved into the implementation of the packaging scheme for our solar power spacecraft. And I showed you a kinematic model to design the folding process. And also we invented this deployment mechanism to control the coiling and uncoiling of the structure. And we demonstrated it on our 2-meter scale structural models. And finally, we looked into the deployment dynamics of the space solar power satellite. And we found that our model can actually capture pretty well the experiments that we did here on the ground. So that's pretty promising. And in terms of contribution, as you can expect, well, this work directly flows into the development of our flight demo, Dolce. Of course, we are folding the structure in the same way that I showed you before. And this folding procedure is actually scalable to larger structures. So as eventually we're going to move towards like implementations of the 60-meter scale that we were aiming to, we can still use the same folding procedure. And the deployment mechanism concept that I showed you before is going to be flown and is going to be demonstrated in space. And we are also trying to extend it to different types of problems. Here, for example, at the bottom, you can see a small coiling apparatus for a single strip that is used for a future deployable antenna. And of course, what I showed you is just the tip of the iceberg. There is much more work to be done. And in particular, there are 2 areas that I think would be interesting to explore. One is the symmetry aspect of the problem. We are dealing with symmetric structures, and throughout my simulations, I showed you symmetric models. And that was mostly true for the most part, it was true. However, perfect symmetry doesn't exist in real system. And so quantifying these effects of deviation of symmetry would help us understand better a real system in space. And also the computational time of the simulation is certainly a bottleneck as you try to scale these simulations to larger structures and more complex problems. And of course, well, there are different approaches that other people are using, for example, adaptive meshing and model reduction techniques. And they promise, they offer a promising solution to combining both computational efficiency with good solution accuracy. And with this, I'd like to acknowledge everyone that has brought me to this point. First of all, Professor Pellegrino for accepting me to this lab and giving me the opportunity to work on such amazing problems and guiding me through all of these challenges. It's really been a bumpy road, and thanks to him, I was able to actually solve these really hard problems. And I'd like to thank my committee, both for the candidacy and the thesis, and for their feedback, and the Dolce team that was really enabled all of this research. Without them, I wouldn't have had these structures to really play with. And also all the GALSIT, all the people in GALSIT who have made my life easier outside research. And the international student program was made my immigration in the US and my wife's also very smooth. And also I'd like to thank all of the people in the current and former people in the Space Structures Lab. Unfortunately, I don't have all of them in the same picture, but I share with them lots of good moments, not only about research, but we had also fun. And they've been like a second family to me in these years. So it was great to share this adventure with them. And also all my friends that I met here in the US, with whom I shared lots of good moments outside research, and they're gonna be missed when I will leave. And my family, my parents and my brother, they supported me through these years. They gave me the chance to really follow my dreams. And so if I'm here today, it's thanks to them. And thanks to my wife, was being extremely understanding with me, especially in these last few months. She was like my bond to the reality. And so thanks to her. And I also want to thank all the friends and the family that is currently following from Italy. And so it's 1 a.m. for them. And thanks all for your support. And with this, I'd like to take any questions if you'd like.
Yes.